Hello, my name is Ida Ang, and I will be presenting on the effect of elastocapillarity on the swelling kinetics of hydrogels. Hydrogels consist of cross-linked networks of polymer chains saturated with solvent molecules such that they experience coupled diffusion and large deformations. Understanding the swelling kinetics of hydrogels is important for many applications, from biomedical, such as drug delivery and wound healing, to flexible electronics. Illustrated in this image from Bertrand et al. Is an example of a hydrogel microsphere swelling over time when placed in solvent. Understanding these time-dependent kinetics are important when fabricating micro or nanoparticles which will release a drug agent of interest during the swelling process. The novelty of this work lies in the consideration of surface stresses which can significantly influence soft materials at sub-millimeter length scales and at low moduli. In engineering material systems, we usually only consider surface effects in the nanoscale for soft solids, but recently, as shown in this figure from Style et al., surface elasticity has been proven to be significant in the millimeter length scale. This image shows surface stresses having a stronger effect on fluid inclusions within a stretched soft solid at smaller length scales, allowing it to retain its spherical shape. In general, the relative importance of surface stresses is based on the elastocapillary length scale, which is a ratio of surface energy to the instantaneous shear modulus. In the next slides, I will briefly present a novel nonlinear theory and mixed finite element formulation that takes into account mass transport, large deformations, and elastocapillary effects. I state here the governing equations, otherwise known as the strong forms. Mechanical equilibrium is maintained within the volume, surface, and boundary curves. P is the first Piola-Kirchhoff or nominal stress. Surface terms are indicated by a bar, where this is the surface divergence of the surface first pk stress. The double brackets of the last equation indicate summation over the two surfaces that intersect on the boundary curve, where n bar is the binormal vector to the boundary curve L. N is the normal vector to the surface. The body force is denoted by B naught, and prescribed terms are denoted by checks, where we have prescribed tractions and displacement. In our schematic, we note that the initial state is not coincident with the reference state and demonstrates the smoothing of sharp boundary edges through application of surface energy. The mass conservation equation is stated where C is the nominal concentration, J is the nominal flux, and R and I are source terms for the number of small molecules through a volume and surface element respectively. Mu is chemical potential. To prepare for our mixed finite element formulation, we can obtain the weak forms from the strong forms, where the primary unknowns are a vector field of displacement and a scalar field of chemical potential. For more detail on this formulation, see Hong 2008. The term accounting for surface effects is shown, and we can use the implicit backwards Euler scheme to integrate the second equation over time. No superscript refers to the past time step, and a superscript refers to the current time step. Now we can define specific free energies of the volume according to Flory-Renner theory. We have a free energy associated with elastic stretching of polymer chains and a free energy of mixing of polymer and solvent molecules. The first is listed, where N is the effective number of polymer chains per unit volume of the polymer. Kb is Boltzmann's constant, T is temperature, and this is the first invariant of the Wright-Cauchy-Green tensor. The free energy of polymer-solvent mixing is defined where omega is the volume of a solvent molecule and the Flory parameter is given as chi, governing how likely solvent molecules are to enter or leave the hydrogel. We assume that the hydrogel volume changes only through solvent diffusion, considering that the hydrogel constituents are individually incompressible. With nano and microparticle drug delivery systems in mind, we consider a unit sphere for our model setup. In the prior slide, we had defined bulk free energies, but here we define the surface free energy density, which is given where gamma is a constant surface energy per unit deformed area, otherwise known as a fluid-like surface energy, and J bar is the surface Jacobian. The sphere is traction-free, and our boundary conditions prevent free translation and rotation. The model is a unit sphere in its reference state. At its initial configuration, the sphere is at a homogeneously swollen state with initial stretch, lambda naught, and initial chemical potential, denoted by this expression. An example of how this state can be achieved physically is by placing the microsphere in a humid environment for some time. Following this initial state, the sphere is immersed in solvent of a different chemical potential to its initial value. This change in chemical potential causes a certain degree of swelling or drying depending on the initial stress, Florey's parameter, and gamma. Taking into account surface energy in this initial condition yields this red term. Focusing on hydrogel microspheres, we provide a comparison between the nonlinear theory and an analytical solution using the theory of linear poroelasticity that incorporates surface stresses. This comparison is important for validation of our nonlinear theory. So this plot tracks the radius over time normalized by the initial radius. In this figure, the material parameters for the simulations were chosen to keep the strain at equilibrium below 5%, where we expect the results to compare closely. The asterisks indicate the normalized time to 99% equilibrium swelling. We can see that the nonlinear and linear theory results compare closely for small deformations in both final radius and time to equilibrium. In figure B, the red and blue lines show simulations where the material parameters were chosen to keep the strain above 5%. We can see that at large deformations, not only does the radius not match, but the time to equilibrium does not match. The yellow case demonstrates a case with a high surface energy value leading to significant elastocapillary effects, where the final radius matches, but the time to equilibrium does not match. Overall, these images show that for large deformations and significant elastocapillary effects, linear theory is not sufficient for predictions of the transient response. Now that we know our theory is validated for small deformations, we can consider large deformation cases of the microsphere problem where a normalized surface energy value leads to an elastocapillary number of 1. Now, dashed lines show cases without surface energy, and solid lines refer to cases with surface energy. This image demonstrates normalized time versus radius, and we can see regardless of swelling or drying, the equilibration time is almost an order of magnitude smaller when surface stresses are present. Up to this point, we have been considering constant surface energy per unit deformed area. But what if we consider a more complex material response, such as a neo-Hookean surface energy? In these plots, the red dashed line indicates the case without any surface energy for comparison to a case with significant constant surface energy. And recall, this is the associated surface free energy density. The blue cases indicate cases where a neo-Hookean surface energy is prescribed and the related free energy density is given, where lambda b is the area modulus and mu b is the surface shear modulus. Just as shown in the slide before, the constant surface energy case shows a faster time to equilibrium, but now we can observe that for cases with similar final deformation, a neo-Hookean surface energy yields an even faster equilibration time. These results indicate that neglecting surface elasticity of hydrogel microspheres may significantly overestimate equilibration time. In conclusion, elastocapillary effects significantly alter the swelling and drying kinetics of hydrogel microspheres, which is important for drug delivery systems. Not only do we observe faster equilibration for a constant fluid-like surface energy, but also by considering surface elasticity, we predict even faster diffusion kinetics. Predicting the deformations and time evolution of spheres, as well as more complex constrained structures, shown here, is advantageous when considering design of microscale applications, which not only cover drug-releasing nano and microspheres, but also pneumatic systems and actuators for soft robotics. Thank you for listening. I would like to acknowledge my funding source for the NSF, and any questions can be directed to my email.